All right, good morning. I'm going to kind of review everything that we've done in this unit so far from the top. And although some of the introductory stuff I'm going to talk about here is not that crucial for today, it's a pretty sequential sequence of things we've learned. What we're going to learn today kind of starts putting everything together. So we started with what's called the Dalton model of the atom. The Dalton model of the atom is very childlike in its simplicity. It simply says that, oh, guess what? Everything's made of these things called atoms. Atoms are indivisible. And each element has a different atom of some kind. You know, if you were to ask Dalton, I've never found the answer to this. I suspect Dalton would say that what distinguishes a hydrogen atom from a helium atom is the size of the thing. Okay, I don't think there's any other real difference you could talk about. When electrons were discovered, Thomson, after his discovery of electrons or quantification of these cathode ray particles, which we now call electrons, Thomson incorporated those electrons into the model of the atom that was current, which was Dalton's. And we don't really talk about why this sphere is fluid-like, is gelatinous-like in some way, but it has to do with the density of matter. And the only way this model can make sense is if you have not a solid, crunchy kind of sphere, but a globule of stuff. Okay, it's very low density. And then the reason why it has to be positive is because these negative particles, which are very, very tiny, are negative. So atoms are neutral, you need a positive part of the atom, and that's kind of the bulk of the atom. But it fails to explain alpha scattering experiments, which we talked about yesterday. So look, in the end, when you send alpha particles through a very thin piece of gold foil, they just don't do what they would do if atoms were like this. They don't behave like they would behave if atoms were like this. They behave as if atoms are mostly empty space with a very, very concentrated, large amount of the matter or the mass in a very small place called the nucleus, and it's positive, and the negative particles or electrons are at very, very large distances. We ended yesterday by saying that when you look at, and I have a hydrogen light source here, and somebody's already pointed out to me this morning, this looks pretty precarious. It's solid, okay? It's not just balanced there on a piece of wood. I have magnets all over the place that are securing it in place. So it looks like something that I just tossed together and crossed my fingers that it wouldn't fall apart, but it's secure. We saw yesterday when you look through a diffraction grating at that and spread out that pink light that the hydrogen gas is emitting, that it emits 4 specific colors or wavelengths. Now, I don't know if I asked, did anybody see the 4th color? I think it's almost impossible in this room to see it. But you definitely saw the red and the green. Probably, I think everybody saw the blue, but you might not see the blue. But the violet was very, very difficult to see. In the end, hydrogen, which is what's inside of here, it's atomic hydrogen in here, by the way. It's not hydrogen molecules, it's hydrogen atoms. It actually is hydrogen molecules, but when I turn on the high voltage of about 10,000 volts, it breaks the molecular bond, and we just have free atoms moving around. Hydrogen atoms contain a single proton and a single electron, and if Rutherford's going to claim that what's happening is the proton is the nucleus, which it is, and the electron is in some kind of orbit around it, he's got to explain why you get these 4 wavelengths of light. He's also got to explain why, and he can't with this model of the atom, why is it that in every other circumstance in the universe, I'm talking about the bottom statement here, in every other circumstance in the universe, when you have charged particles like electrons accelerating in any way, you continually produce EMR. Like, right now I have the voltage off. There's hydrogen atoms in here. Rutherford's claiming the electrons in the atoms are going in circular orbits, so they're accelerating. This should be emitting EMR right now, and it doesn't. So Review a few other things. This is the bottom line for Rutherford's nuclear model. That's what it looks like. That's what we can visualize it as. In the nucleus, it's not just a positive thing. It's positive nucleus that contains protons and neutrons. And again, it cannot explain the line spectra, and it violates Maxwell's principles of electromagnetism. So now we're leading up to today's topic. There are three types of spectra. A continuous spectrum of light is produced by a hot, glowing solid. A bright line spectrum, like the one we're looking at here. Well, you're not seeing the spectrum because you don't have a diffraction grating to look through right now. But the light emitted here is a bright line spectrum, and a dark line spectrum is, I've got produced in kind of quotes there, when white light passes through a cool gas, what makes it out the other side is a dark line spectrum or absorption spectrum. So this is what they look like. I think these are computer generated. Under ideal situations, you might be able to see the violet in this room, but it would be very, very difficult. By the way, this bright line spectrum happens to be the bright line spectrum for the hydrogen. So when I do this, I'm telling you that those four wavelengths are the only wavelengths that are coming out. And if I were to shine, we had a discussion about how you could do this. If I were to shine white light that was from a continuous spectrum or a hot glowing solid through this tube when it's not lit up, and then I analyze the light that comes out the other side, I would discover that the hydrogen gas swallowed up the exact wavelengths that it would emit if I turn it on. So there's only allowable energies or photon energies that hydrogen can emit or absorb. Here's a cartoon-like graphic just demonstrating what's necessary. You have a black body, which is a solid glowing material, going through a diffraction grating. I say cartoon-like because this is not the path that the light, the different colors will take. That's just representing the fact that the diffraction grating splits apart the light. And you get a continuous spectrum. Quality of this graphic is not that good. The hot gas, in terms of clarity, the hot gas produces that type of spectrum, and the cool gas absorbs certain wavelengths from a continuous spectrum. If you were to look at a similar diagram that used a prism to spread out the light, that's what it would look like. Just take that in for a second and understand the only difference between what you're looking at right now on the main screen and what you're looking at on the side screen. They're the same idea, except you're using a diffraction grating in one and a prism in another. So what you're looking at on the main screen uses refraction. What you're looking at over here on the side uses diffraction and interference. A spectrometer, well, a spectrometer is a device that can take this light and spread it apart. So if I want to look at a diffraction grating spectrometer, and this pink light here is this hydrogen light, okay? And I pop a diffraction grating in there, then I get a red n equals 1 on the top and the bottom, I get a green n equals 1, I get a blue n equals 1, and I get a violet n equals 1. If I were to look further up and further down, I would see that whole series of lines again at the n equals 2 positions. So this type of spectrometer can produce, well, it produces multiple spectra, 2 or 4 or 6, etc. However, with, well, I guess I'll talk about this now. We're going to do this calculation in a bit. We're going to have somebody come up here and we're going to read some numbers off of this by looking through a diffraction grating. But if you want to know those wavelengths, you just use Young's double slit formula, right? I mean, you can do this experiment. You can measure X to violet, if you can see the violet. You can measure L, the distance from the diffraction grating to the screen. You can use it to find the angle, and then you can calculate the wavelength. If you use this type of spectrometer, by the way, you would only get one spectrum here. What you can do is measure the angles, and we did this lab as well. It's just that you did it with a single color of light, a laser, like green or red. I think I just had you do it with one laser, didn't I? The Jello? I mean, you might have played around with other lasers, but you only used one for your measurements. You can measure the angle of incidence and the angle of refraction, and knowing the index of refraction of light in the air and knowing the index of refraction, and use that to calculate the index of refraction of the color you're looking at in the glass, and then figure out the wavelength from that. And I realize there's a big gap there in me just saying you find the index of refraction of red light in the glass and then you figure out the wavelength. There's not a formula. You have to go to empirical data. You have to look at a graph, and if you got 1.54 for the index of refraction for the violet wavelength, then like 1.52, then you would get 500 nanometers. You'd have to read it somehow. In the end, if I talk about a diffraction grating, this is what a continuous spectrum looks like. This is what the bright line spectrum looks like. And you'll notice I've given the wavelengths there, which if you're open to the next lesson, they're on the first page of that lesson. And this would be what the corresponding absorption spectrum would look like. So now we're going to get started with today's lesson, which is called the Bohr model of the atom. The Bohr model of the atom is able to explain, I might as well say this right now, the Bohr model of the atom is able to explain, and I'll have to move my periodic table now that we're going to be referring to it, all of the line spectra for hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. It's able to explain the atomic line spectra, these things that we were seeing when we looked through the diffraction grating, for those elements only. Okay? I guess I want to be very careful here. The basics of the Bohr model of the atom will explain all of these spectra. All of the other spectra can still be explained using the basic ideas of the Bohr model of the atom, but Bohr wasn't clever enough to crack the code. I'll put it that way, okay? For you chemistry people, you should understand that all of these elements in group 1A have a similar property, and that's that they have one valence electron. And that's why Bohr is able to very easily easy for him, come up with formulas that predict the line spectra, because he treats that single electron that's a valence electron as a single charge, and he treats everything else as a single charge. But as soon as you have multiple electrons interacting in the outer valence energy level, it's very complicated. So we're going to be working with the Bohr model of the atom. And I've already reviewed this, so I'm going to do this very quickly. The two main problems with Rutherford's model is it violates Maxwell's principles of electromagnetism, which say that accelerating charges ought to produce EMR all the time, and atoms do not do that. Let me add something to that. The reason why that's important is Rutherford is claiming electrons are accelerating in circular orbits. So they ought to emit EMR all the time, but they don't. So they can't be accelerating in circular orbits. And it cannot explain what you see when you look through a diffraction grating at a bright line, to see a bright line spectrum. So it turns out that these are the 4 wavelengths. And what I actually have up here is, a graphic that doesn't have colors. And I think it might be the case that yours is in the opposite direction. No, yours is in the same direction. Red on the left? Okay. What I have here is a computer-generated image. And what I have here is a photograph taken in a typical physics lab. You would really, really, really need to see this last line in particular, almost total darkness. And you'll notice that in the photograph at the bottom, the one that's supposed to be green is overtaken by some blue light in the surrounding area. All of this in here, the colors mean nothing here. All of this in here and in here is just what we would call ambient light in the room when the photograph was taken through the diffraction grating. And the fact that this blue light here is overcoming the green color means that the green is very faint. There's not a lot of green light. And by the way, one of the reasons why it's difficult for you to see, impossible in this room, for you to see the violet color when you look through the diffraction grating, one of the reasons is your eyes are not too sensitive to that wavelength, but the other is there's not a lot of that light. When I light up this hydrogen, it emits more red light than it does violet light. There's more of the red photons coming off than there are of the violet photons coming off. It isn't an equal share of the light. So those are the wavelengths. We're going to do a little experiment right now. So we're going to actually calculate those wavelengths by measuring things. So I need somebody with good eyes. Sure. So what you're going to do is you're going to have a seat here. We're going to be using this diffraction grating, or you can... Which way do I want to go here? I want to go this way. So what you're going to do is look through that window. You're going to, just before we take any measurements though, you're going to make sure that window is pretty much across from there, like not over here and not over here. Yeah. And you're going to position your eye so that you don't have to move your head to see the lines on the left and the right. Because as soon as you move your head, then everything shifts. Okay? And what we are looking at, we're going to start with the red. Can you see, when you look through, can you see the red line on the left and the red line on the right? Yep. Okay, so what you're going to be doing is telling me what the distance is. These 2 meter sticks are centered and start at 0 on in right dead center. You're going to read to me the X value for the red on the right and the red on the left.
Okay. Right? Yeah.
Yep.
17. And also 17.
Okay, that's good. That means everything is nice and square. Because if Carly turns the diffraction grating like this to over-exaggerate it, then the triangles won't be similar and you'll get different lines. But if we do get different line lengths, that's okay, we'll just average them. Can you take a look now at the green, please?
Like 12 and a half-ish?
12.5?
Yeah. And like 12.3 on the other
Okay, and without moving the diffraction grating, can you see the blue?
Yeah.
You can, okay.
Yeah.
Go ahead.
Around 11.
So,
maybe 10.8 or something.
okay, so we want to be as precise as possible, to the nearest millimeter probably, yeah.
Yeah.
Okay.
And the next one's right on 11.
Right at 11, okay. And I don't know if you'll be able to strain your eye without moving your head, without keeping your eye in the same, your head in the same position. You'll be able to strain your eye to the left and the right enough to see the n equals 2 images. If not, we don't need to. No?
No.
Okay, that's good. And this is from, thank you very much, Carly. This is from a different semester where I maybe used a different diffraction grating that would allow us to, the lines were closer together, okay? By the way, this is 300 lines per millimeter, and this is the value of D, and you're going to be doing some calculations right now for me. And you've done this lab before. I looked at where Carly was holding the diffraction grating. It wasn't right on the edge there, so I'm going to measure L. And I'm going to say L is 84 centimeters. So 0.84 meters. If you average 10.8 and 11, you get 10.9 centimeters. If you average 12.5 and 12.3, you get 12.4 centimeters. These average out to 17, and we're not doing this. So the first thing you would need to do is ask yourself if we can use lambda equals xd over nl to determine the wavelengths, which we're trying to determine here. Well, you have to do a tangent calculation. If I were to look down this way and then take that, what I see, and put it vertically up, This is the top of Carly's head. This is her line of sight. Here's the diffraction grating. This is your X and this is your L. And then there's an X on the other side, but we've averaged it. So I think it's pretty clear you're going to get probably more than 10 degrees. And look, even if you don't, why wouldn't we find the angle and use the precise formula anyway? So what you need to do, and I'm going to give you 4 or 5 minutes to get some numbers here, is you need to use tangent of theta equals x over L to find theta for each of these. And then you need to use lambda equals d sine theta over n. And we're only doing the n equals 1, so you're going to be using n equals 1. And you want to do that to find the wavelength, and the wavelength that you find is going to be obviously different for each of those 3 colors. And I didn't ask Carly, but there's no way you could have seen the violet.
No,
No. You could see the blue, but it wasn't very bright. Well, you could tell there was something there, but yeah. I'll do the calculations as well. By the way, if you're going to use, when you use tangent to find the angle, you have to use meters over meters or centimeters over centimeters. You can't mix and match. Wow. Those of you that are, has anybody got all 3? Same numbers? I'm saying wow because that's really pretty close. Take a look at the wavelengths on the handout. I mean, it's not going to be perfect. Let's face it, this thing is just kind of rigged up, and this might have moved a little bit, and the diffraction grating might be a little off, and all kinds of issues at play here. But what should the wavelength of the blue be? I think 434. So we're getting 429. I mean, you're 5 nanometers off. If I were to look at a percentage error, I could take that 429 and subtract 434 and then divide by 434 and multiply by 100. We're like 1.2% lower than what it should be. So imagine how precise you could get if you actually had a spectroscope that was locked down on a stand and you can measure the angles very precisely. Can you tell me what the green wavelength should be?
486.
Bang on, 486, 0% error. Now, we do have to chalk that up to precision and good reading of the data. There's got to be some error here, so there's positive and negative error canceled out. But that doesn't take away the fact that the data was collected beautifully. 660, I think it should be, I don't remember, 656. That's an even smaller percentage error because it's only 4 nanometers and it's 4 nanometers out of a even bigger wavelength. You said 456? 656 rather, yeah. So 660 minus 656 We're 4 nanometers too high this time. That means our percentage error will be positive, so divided by 656 and times 100. I mean, less than a percentage error. Doesn't get much better than that. So we had like 1.2% off, 0%, and 4%. I don't know that you should really be averaging percent errors, but why not? On average, our average percent error was 0.6%. So it's very, very accurate. Now we have to explain where these wavelengths come from, and that's the bulk of today's lesson. Niels Bohr is the physicist who came up with the ideas that explain why those wavelengths of light are emitted. And I'm going to go through his thinking here and just highlight for you the important points that you need to know. There he is. I think this is obviously when he was very young, maybe a first-year university student, and then at the end of his career, making up some kind of alien language on the blackboard there. I'm joking, that's math. It's higher level math. Which tells you, and the reason I put that picture is this, it tells you that the math needed to explain Bohr's models and theories is beyond us. So we're starting to step away from doing a lot of work with equations. 3 basic ideas in Bohr's model of the atom. His first idea is that electrons are allowed to orbit an atom, but only at certain specific distances. What does that mean? It means an electron can be in this orbit, or it can be in this orbit, but it can't be in between, which is mind-blowing right there, because the electrons can dance around from orbit to orbit, but there's only specific places that they can be. And it turns out that these radii are multiples of the radius of the first orbit. So whatever the radius of the first orbit in hydrogen is, it turns out that the second allowable radius is 4 times greater. And whatever the radius of the first orbit in hydrogen is, it turns out that the third orbit is 9 times greater. Does anybody want to take a stab at how many times greater the fourth orbit is than the first? 16. It's a quadratic relationship. And all of those atoms I indicated, hydrogen, lithium, potassium, rubidium, cesium, francium, I got them all. Lithium, maybe I missed. They all follow that same rule. But the first orbit of hydrogen is different than the first orbit of lithium. And the first orbit of cesium is different than the first orbit of hydrogen and lithium. But the second orbit of each one is always that number that the orbit is squared. And we say then that the orbits are quantized. They can only have certain values. And that's what it looks like. And it turns out, you do not need to write this down. But this is the radius of the first orbit of hydrogen, according to Bohr. And it is true. So if I want to find the radius of the second orbit, I would multiply that by 2 squared. Third orbit, multiply it by 3 squared. I have seen on diploma exams them test your understanding of this relationship. Not the equation, but the visual graph, that the radii keep getting bigger and bigger and bigger. So this is what we're talking about here. This is just the first 4. We prefer to use the word energy level or the phrase energy level here. So there's an electron in the first energy level. You see the little blue dot? I've drawn it bigger than the nucleus, which it isn't, just so you can see it. The electron is allowed to be there. The electron is allowed to be in this orbit, or energy level. The electron is allowed to be here. The electron is allowed to be there. But it is not allowed to be in between, which should bother you a little bit. Because if I tell you it can go from the fourth energy level to the third energy level, but it can't be in between, what I am telling you is that it ceases to exist in the fourth energy level and then appears in the third. And that is what happens. Okay? It's not just a way to wrap our head around it. That is physically what happens. It's the only explanation for what's going on. Now, the second point is that the electron in orbit around the atom will have energy. It's moving, so it has kinetic energy, and it's attracted to the nucleus, so it has potential energy. Just like the calculator I'm holding is attracted to the Earth, it has gravitational potential energy. So the electron has a sum of kinetic and potential energies. I hope you understand, just even based on thinking of satellites that are in motion because of gravity, that the speed of an orbiting object depends on how close or far away it is from the center. And we know that potential energy, gravitational anyway, of my calculator depends on how far it is away from the center of the Earth. So if the electrical potential energy and the kinetic energy are both related to the distance, but the distance is quantized, the distance can only be these numbers, then that means the energy that the electron has is quantized. So not only does the electron go from being a certain distance away to magically being a different distance away, it goes from having a certain amount of energy to having a different amount of energy. This is crucial to the line spectra. The electron will lose energy when it goes to a smaller energy level, but it doesn't bleed it out gradually. If it loses X amount of joules in going from this energy level to this energy level, then X amount of joules is spit out at once as a photon, turns out. But I'm getting a little ahead of myself. Remember, one of the problems with Rutherford's model of the atom is Rutherford's model would predict that EMR would be continually produced. How does Bohr solve that problem? He just says it doesn't happen. Electrons are allowed to be in an orbit without radiating energy, without losing energy. What he's saying is there's an exception to Maxwell's principles of production of EMR, and that's that electrons in atoms are special. Okay? It's not a very satisfying solution to the problem, but if we accept that it's true, everything else falls into place. We often call these, I want to highlight this phrase for you, and that's gone. We often call these energy levels stationary states, and it's not because the electron isn't moving, it's because the energy is constant. So when you see that phrase, stationary state, it doesn't mean that it's physically stationary, it means the energy is constant. I just want to fix something here quickly. It will only take a second. Good. All right, so I'm going to hand out what's called an energy level diagram for hydrogen. So we do not, I'll show it to you up here. This is the energy level diagram for hydrogen, or an energy level diagram for hydrogen. Where the math is in another arena of our universe and we're not going to worry about is how we get these numbers. Bohr gets these numbers somehow. Okay, we don't need to worry about it. I might at some point kind of give you an inkling as to where the numbers come from. But it's not important. It's not important today. It's not important for the rest of the course that you know where these numbers come from. I know I asked this yesterday, but I'm curious because I can't remember the answer. On that color printout on page 15, can you see the violet? Or are you just deluding yourself into believing that you can see something? It's pretty, how many of you feel as though it's there? Okay, amazing eyes. So it's a good thing I put that little line that says violet is here. We have to, did everybody get one of these? Okay, we have to understand something in general about this energy level diagram that you're looking at. All of the numbers are negative. Can you see that on the handout I just gave you? How can we have a negative energy? Well, I'm going to go back very briefly to Physics 20. If I were to say to you, does this calculator right now on top of this stool have gravitational potential energy? I think every reasonable person would say yes. I'm not saying if you said no, you're unreasonable. But I think it's reasonable to say yes, because it's above the floor, right? If I were to say to you, when I put the calculator on the floor, does the calculator have gravitational potential energy? Most reasonable people would say no. But what if I told you there's a basement in this building? And there is. There's a door just around the corner here. You can go down. There's stairs that go down. Got a pool table, some pinball machines. I'm kidding. It's got the furnace and all that other mechanical stuff for the building. Does this calculator have gravitational potential energy relative to the basement? Yes. It's very similar, everybody, to having a pendulum. And if I'm swinging a pendulum around, I guess I'll just swing this. If I'm swinging a pendulum back and forth, if I'm interested in knowing the speed that the pendulum has at the bottom of the swing, I say that there's no gravitational potential energy at the bottom. It makes my calculations easier. Because this energy is a sum of kinetic and potential energies, and potential can be negative, even though kinetic cannot, we can put 0 wherever we want. Okay? And we like to put 0 at the top. And you should make a note that E infinity, there's an infinite number of energy levels. E infinity is where the electron is no longer part of the atom. It's free. And that's why I have on my diagram, and I don't know if I put it on yours, I didn't, right above the line that represents E infinity, I've got ionization state. If we can get an electron in an atom to be there, we have ionized the electron from the atom, which means the electron is free. On the other hand, if the electron is in the first energy level, which corresponds to a radius of orbit, then it is in what we call the ground state. It's in the lowest, most stable position it can be in. And I can call 0 wherever I like. So the reason why we put 0 up top here is it makes sense in terms of the atom. If that's where the electron is, it has no energy compared to the atom. However, if you turn your sheet of paper over, and I lost the page here, I don't know why, but if you turn your sheet of paper over, you see the same diagram, but the numbers are different. Go ahead and take, on your calculator, 13.6 plus negative 13.6. What do you get? 0, which is the E1 on the back side of the sheet. Go ahead and take negative 3.4 plus 13.6. You get 10.2, I think. And that's what E2 is on the other side. I want us just to do one thing before we finish this lesson off and do calculations. Do me a favor, look at the front side of the sheet and pick 2 of those energy levels, any 2 of those energy levels. And take the one that's above minus the one that's below. And you all might have different numbers, right? You might have picked E7 and E4. But I want you to turn the sheet over and pick those same 2 energy levels and subtract the numbers that are there. The number that's above minus the number that's below. You get the same number, right? It is not the value of any individual electron's energy that is important when we talk about line spectra. It's how much energy is lost or gained. So that leads us to the final idea. An electron can move from one energy level to another as long as it loses the difference between those two energies or gains the difference between them. And there's going to be a little exception to this later, but the energy change is always accompanied by the emission or absorption of a photon. So if I go back to my energy levels, if I have in any atom, this happens to be hydrogen I'm talking about, an electron that is in the second energy level and it goes down to the first energy level, that electron has lost an amount of energy. Whatever that energy the electron has lost is accounted for because a photon comes out of nowhere and leaves the atom, and the photon energy is equal to that difference. If, on the other hand, I have an electron in the second energy level, and for some reason it pops up to the third energy level, then it has gained energy. And whatever the difference between the third and the second energy level is, that's the energy gained. How did it gain it? It absorbed a photon. Are you starting to see why the bright line spectrum has certain wavelengths that are emitted, but the dark line spectrum has the same wavelengths that are absorbed? When an electron falls or jumps, we use the word jump sometimes, from 3 to 2, when it jumps from 3 to 2, it loses an amount of energy, and that would mean a photon is emitted with that energy. If this electron jumps from 2 to 3, the electron gains that amount of energy, which means a photon has to be absorbed with that same energy. So the photons that it can emit and the photons it can absorb are the same. In the end, when this happens, there's a photon emitted. And you can actually turn the page. When this happens, a photon is emitted. When this happens, a photon is absorbed. And I draw that arrow, but it's not like traveling from Edmonton to Vermilion and passing through, I don't know, can't think of it, Vegreville and Manville along the way. You don't stop. You're transported immediately from Edmonton to Vermilion. I don't know why I thought Vermilion. If you don't know where that is, don't worry about it. Okay, so questions. An electron in an atom drops to a lower energy level. The initial energy level was 2.24 electron volts higher than the final. So what happens? Somebody tell me what happens. There's a number of things we could put here. Annalie? No, a photon is emitted because the electron goes from an energy level and it drops to a lower. So think when you climb a hill, there's more energy. It's more complicated than that, but when you have a higher energy level, there's more energy. And you might see that easier if you look at the positive side of your hydrogen energy level diagram. As you go up, the numbers get bigger. But by the way, as you go up on the negative side, the numbers get bigger too, don't they? From negative 13.6 to negative 3.4 is an increase. So a photon is emitted. Can anybody tell me anything about the photon that's emitted? Jack?
It will have an energy of 2.24 electron volts.
Absolutely. A 2.24 eV photon is emitted. Because however much energy the electron loses, that's the energy of the photon that's emitted. Well, you can tell me the wavelength now. Because E equals hc over lambda, and 1242 eV nanometers is our friend here. We do not want to be messing around with entering Planck's constant in the speed of light. We just take 1242 divided by 2.24, and we'll get the wavelength. a 555 nanometer photon is emitted. You get the same number? Greenish, probably. Might be getting close to blue. I just know it's greenish because the green lasers we use are 532. So I'm guessing 552 would be still kind of greeny in nature. Maybe teal, maybe starting to turn into blue. An atom absorbs an 850 nanometer photon. First of all, that means the atom is allowed to absorb an 850 nanometer photon. That means there are two energy levels in the atom which have an energy difference equal to whatever that energy is. So we want to think in terms of energy. If E equals hc over lambda, then we can go 1242 eV nanometers divided by 850. I just want to back up for a second. I didn't mean to skip over something here. If you rearrange this equation for lambda, you get that, and that's what we did to calculate the wavelength in question 1. Over here, 1242 over 850. Well, this photon had 1.46 eV of energy. What does this mean? Whoop. Oh. Who knew that was even there? It means, did I just say 1.46? The atom gains 1.46 eV. And what that means, I don't want to spend too much time with all these questions, but what that means is somewhere in the atom are two energy levels that differ by exactly 1.46 eV because it's allowed to gain that much energy. An atom can emit a 120 nanometer photon. What does this tell us about the structure of that atom? Well, we want to think energy, so I'm not even going to write down how we do this. I would like you to calculate the electron volt energy of this photon that the atom is capable of emitting. And I know it's going to be a little bit more than 10. 10 point what, Ashley? 10.35. So I'm going to round that to 10.4 eV. What does this tell us about the structure of the atom? Somewhere there is a lower energy level and an upper energy level where E upper minus E lower has to equal 10.4 eV. Are there other energy levels in the atom? Of course. I mean, there might be energy levels here and up here. There might be one in here. And just to go back to Bohr, Bohr would not be able to explain where these energy levels are unless it's one of those 6 or 7 group 1A elements or atoms. Why is it then, let's imagine that we looked through the diffraction grating yesterday at this pink light, which is the hydrogen light, and let's imagine you could see that fourth line. Why are there only 4 lines that we can see? Because I'm telling you, you got the energy level diagram, there's an infinite, theoretically there's an infinite number of energy levels. So there's an infinite number of different transitions the electrons in hydrogen can make. Will? Those are the only 4 lines where those energy differences are visible. Your assignment today is going to be focused on learning about that, but this is the bottom line. I'm going to come back and talk about this a little bit more later, but I want to keep focused here on our lesson. If you were to take any two energy levels from your energy level diagram for hydrogen, subtract them, and find a wavelength of light that corresponds to that, and you just did that all day long, you would only stumble across the 4 wavelengths that are on the previous page. You would also get some infrared wavelengths, and you'd also get some ultraviolet wavelengths, but you would never get any other visible. What transition would have to happen in an atom to get the wavelength that's short as possible? Jack?
From the highest possible energy level to the lowest possible energy
Right.
level.
Short wavelength is a lot of energy, so from the top to the bottom. From E infinity down to E1. The smallest wavelength is the most energy. When we look at these diagrams at the top of the page, question 6 says, how do the wavelengths and frequencies of these photons compare? So I have, going from 5 to 3, I have a photon emitted. And over here I have an electron going from the n equals 2 to the n equals 6. I have a photon being absorbed. How do the two photons compare? Are the wavelengths going to be the same? Are the frequencies going to be the same? Miles, which of those do you think would have a higher frequency?
Energy moving to N3.
Which one? The one on the left or the one on the right? Remember, everybody, that frequency is related to energy. So the more energy involved, the higher the frequency.
Okay, so it's going to be N6 on the right.
Yeah, the one on the right. Because, look, I hope you can see that this energy is smaller than this energy. So the energy change of the electron on the right is greater, and what that means is you're going to have a higher frequency here than you have here, and I'm exaggerating it, but that means you're going to have a longer wavelength than you do here. And now we're just going to do some calculation questions. And you are going to need your hydrogen energy level diagram for some of this work. So, what is the wavelength of a photon emitted when an electron goes from the 7th to the 3rd energy level? If I've done a half-decent job, this is something that you should be able to do on your calculator. I'm going to write down what we're doing. But what we're saying is the energy of the photon, and in this case, Annalee, is the photon going to be emitted or absorbed? It's going from 7 down to 3. Emitted, right. And that's one of the tricky things. We're going to get really good with the numbers, but we can't forget that to go from a higher to a lower is photon emission, and photon absorption means the photon is being absorbed, it's disappearing, jacks the electron up. This has to be equal to the change in the energy of the electron in the atom. So really, and I don't think you need to make this into a complicated formula, but really what we're doing is you're taking the upper energy level minus the lower energy level, and whatever that is, you're setting it equal to hc over lambda. I hesitate in writing that because I don't want you to think we're going to put all these numbers in and rearrange this equation. You go to your formula sheet, you take E7 minus E3, and you go 1242 divided by that. And by the way, energy level diagrams can also be given in joules, but electron volts are more convenient. So my energy level diagram I have up here is not spaced properly in terms of energy, but it doesn't matter. Negative 0.278 minus negative 1.511. So I include the negatives. Do that again. And I'm going to take a stab in the dark here and say that my numbers up here probably don't match the numbers on your sheet exactly. Or do they? They do. No, I think it was maybe just negative 1.51 instead of negative 1.511. Yeah. So my numbers are going to be slightly off from yours. But when I subtract, what I'm getting is 1.233 EV. When you subtract yours, what did you get, Carly?
Like, way bigger, 1,007.
So you probably missed the decimal. Just look at what you've entered.
Oh, never mind, I got 1.2. That was after I divided by 12.
Okay, yeah, we're not done. This is the energy change of the electron. Which means the electron loses that much energy. Did you get 1.233 or did you get something slightly different? Oh, you got that, okay. And now I can just say, well, if that's equal to hc over lambda, then I can take 1242 divided by that energy to get the wavelength. Oh, we're talking about an infrared photon of wavelength 1,007 nanometers. What's the minimum wavelength of light that can be emitted by a hydrogen atom? Well, we already discussed this. The minimum wavelength is the most energy, and that means the electron has to lose as much energy. So we have an electron that is free, all of a sudden tunneling down immediately to the ground state, which means the energy change of the electron would be 13.6 eV. And that means the energy of the photon is 13.6 eV. And I'm just going under an assumption here that you can take the electron volt energy of a photon and find the wavelength in nanometers. It's just 1242 over that number. So about 91 nanometers, which is definitely ultraviolet. Any questions with that one? I only put this question for Math 30 students, and I think there's only one student in the class, maybe two, that have completed Math 30. Who's completed Math 30? One. So I just find an interesting connection here between math and physics. If you only were looking at 5 energy levels, how many different photons could be emitted? Well, a photon is emitted whenever you take 2 energy levels and talk about a transition. So this would be 1 photon. This is almost a puzzle. How many different pairs can you get here? See if you can add them up. Put up your hand if you think you know when you get it. Do you know, Darius? No? Carly?
Is it 10?
It is 10. I'll show them to you. From the top energy level, 1, 2, 3, 4. I didn't do that in a very ordered fashion, so maybe I will do it that way so you can see. There's the second possible one. There's the third possible one. There's the fourth. From this energy level, I can go to here, or to here, or to here. From this energy level, I can go from here to here, or I can do that. And if you count them up, there's 10. Ian, do you see that this is 5 choose 2? There's a mathematical way we could have done it, just saying we have 5 items, we want to pick 2 of them or choose 2 of them. And there's a way to use your calculator to figure out what 5 choose 2 is. So if I had 20 energy levels and I said how many different photons could be emitted, you would go 20, choose 2. Just a curiosity's sake. It would be rather than counting 190, you could just do it. What is your assignment? Your assignment is to complete 1 to 3 on page 17. Now let's just take less than a minute and talk about number 3. Number 3 asks you to complete, number 1 asks you to complete this table. You need to find the wavelength of light emitted by hydrogen when an electron goes from 2 to 1, when an electron goes from 3 to 1, from 4 to 1, 5 to 1, 6 to 1, 7 to 1, 3 to 2, 4 to 2, etc. Tell you, if you don't use that 1242 shortcut, you'll be at it all day. You have to subtract the energy levels and then use that energy to find a wavelength. And that's your assignment for tomorrow. I need you to have it done for tomorrow because we start off tomorrow by talking about the results of this table. I also would like you to classify what part of the electromagnetic spectrum each photon is. So in each box you should be writing something like ultraviolet, infrared, visible. You will not get anything in the X-ray or higher. You will not get anything in the microwave or lower. UV, infrared, and visible. And that's your assignment for tomorrow.